Good afternoon, Professor.
Hello, guys. Hi, everyone. I hope the weekend was good for you. Apparently, one of the last weekends before the winter starts. Okay, so not sure. Some people maybe still join, but in any way, it's time to start our discussion. So any questions related to the previous material which we discussed before, or something what you read during the weekend? Good. And if you have any questions, you're welcome to interrupt me. Let me change the camera. Okay. So today, and actually during all this week, we're going to discuss new topic, which is linear momentum and conservation of momentum. This is another important topic in classical mechanics, and in combination with the law of conservation of energy, concept of kinetic and potential energies, which we described and discussed in details during last week. This will be, they will complement each other, this conservation of momentum and energy. So you can proceed further with a wider variety of problems to be solved. So this is important concept in physics, and let us start. So let us consider a constant force. Okay, constant force, constant, and applied to somebody with mass m. As a result, it will, according to the second law of motion, it will move with some constant acceleration, which can be represented as v2 minus v1 divided by delta t. So let us write the second law of motion. In this case will be ma equal to m v2 minus v1 divided by delta t. And this we can rewrite in a bit different form. So it will be product of our external force with delta t equal to mv2 minus mv1. So the quantity, which is equal to the product of mass and velocity, is called momentum. So its vector quantity equal to mass multiply velocity. And this is the definition of linear momentum. And as you see, the units for momentum, they are kilogram times meter divided by second. So it doesn't have its special unit, so it's used like this, kilogram times meter divided by second. And this is the unit of one of linear momentum. So we can now write this equation in terms of difference in momentum. So it will be F delta T multiply equal to P2 minus P1, and this is delta P, change in the momentum. So the left side, so the right side of this equation is like momentum final, momentum initial. So the difference of these two vectors is delta P vector, change in the momentum. But the left side is called impulse of force. So it's a product of force vector multiply the time interval during which this force is exerted on the body. So change in the, from here we see that change in the momentum of the body is equal to the impulse of the force. And obviously the units for like impulse of the force, sometimes it's denoted as capital I, vector equal to F vector delta T, and the units for this impulse of the force is the same as units for momentum, because they are equal to each other in terms of impulse of the force is equal to change of the momentum. So if we consider this like last equation in a limit of delta T approaches 0, so very small change in the time, so we can write that force is equal to first derivative of momentum. And this can be written, we can extract constant mass from momentum from this derivative. So put it in front of the derivative. And this will be the product of mass to the first derivative of velocity, which is acceleration. So this is second law of motion written in the differential form, or sometimes it's called second law of motion in terms of momentum. So we gave the definition of momentum, got the units, how it is measured and defined, explained that change in momentum over time, its derivative over time, gives us the force which is applied to the body. And so far, nothing special is about this momentum. So, okay, we introduced another quantity in physics, which is product of mass and velocity. So what is really neat about momentum and very useful, like has very practical and I would say even fundamental meaning and application. Okay, let's go to next slide and try to figure this out. So it appears that momentum is one of these quantities which comparable to, in this regard, to energy. It's like ratio between kinetic energy and potential energy in the system without non-conservative forces, where we don't have dissipation of energy because of friction. So these two parameters, the sum of kinetic and potential energy, remains constant. Doesn't matter what happens in the system, doesn't matter what changes are going on there, it's always a constant. And of course, it's very convenient because then we can apply this fact to solve different problems and explain different situations and processes. So this similar feature exhibits momentum. So if we have an isolated system, doesn't matter. So isolated means that this system, external forces do not impact on this system, or external forces are compensated. We will consider these definitions a bit later. So of course it's kind of idealistic picture, but if such a system exists, then it can consist of many bodies, many particles, which are moving, so they can change velocity, directions, all this in every given instant of time, all these parameters can be changed. But what is interesting that the sum of the products of mass and velocities will remain always constant. So let us try to show and that this is true. So for this purpose, we will consider two, let's say, balls which are moving on some ground without any friction. And we consider this system to be isolated. There is no external forces applied to this system. So let's say we have small ball with M1 and larger ball with M2. So M1 is moving with some velocity V1 and M2 with some velocity V2. And in this, so this is axis X, so they move in the same direction. And let's assume that V1 is larger than V2. So first body will kind of chase the second one, and at some point it will reach it. So these bodies will start to interact with each other. So let's consider this moment of interaction. So we will have a contact between larger and smaller. And this force, which describes the interaction between two bodies, of course, it will not be constant. So it will change in time, but we will consider a very short interval of time within this force can be of interaction can be considered as constant. And then we will consider each moment of like proceed further with these small intervals of time and integrate it eventually to get the total change in momentum. So at some instant, like very short interval of time, we have two forces. So it will be force 1, 2, and force 2, 1. So it's how second body applies some force to the first body, will be force 1, 2, and force F2, 1. It's how first body applies some force to second body. According to, so they interacted, and after this interaction, we have a case 3, so they detached. And continue to move, but they change their velocity. So body M1 is moving after this collision with some velocity V1 prime, and body 2 with some velocity V2 prime. So here we will denote velocities after collision as with this mark prime. So without prime is velocities before collision, and with prime velocities after collision. Okay, so let us write down the change in momentum of body M1 during this very short period of time, delta t. So according to our definitions, which we just gave on the previous slide, we can write that F one, 2 delta t times delta t is equal to delta p 1. So it's the impulse of the force, which is the product of force which is exerted on the body, to the time interval delta t is equal to the change of the momentum of this body. So the same we can write for the second body. So it will be force 2, 1 delta t equal to delta p2. Okay, now let us sum these equations together and let's see what we get. So we have F12 plus F21 times delta t equal to delta p1 plus delta p2. Good. So what can we say about forces F12 and F21? In every moment, like instant of time, according to the third law of motion, F12 is equal to minus F21. Because if one body applies some force to the second body will react with the same force, but in the opposite direction. So that is what the third law of motion tells us. We apply this concept here and means that this sum in parentheses will be equal to 0. These forces compensate each other. So if this is equal to 0, then we can write that delta P1 plus delta P2 is equal to 0. So what does it mean? That within this short interval of time delta t, total change in the momentum of these two bodies is equal to 0. So, okay, now we want to know what will happen after all time of interaction when these bodies will detach from each other and then move with some resultant velocities. So for that purpose, let us consider now that interaction will happen during time delta t, which is much larger than this like dt. So delta t is much larger than dt. Then we need to integrate this equation over time, and that will be 0. From 0, let's consider that interaction started at 0 time, then from 0 to delta t, t1 plus integral 0 delta t dp2. It's also, so eventually it will be maybe not enough space here. Let us rewrite this part on the next slide. It will be more convenient. So 0 delta t dp1 plus integral 0 delta t dp2 will be equal to the difference between final momentum of the first body and the initial momentum. So we can write P1 prime minus P1. So P1 is the initial momentum of the body. P prime 1 is the final momentum. Then sum to the same difference between final momentum of the second body and its initial momentum. And this is equal to 0, because if we have no change in momentum at a very short interval of time, so if we add all these 0 changes in momentum for many short intervals of time, for longer interval of time, it will also remain 0, because 0 plus 0 gives you 0. So this is what we get for the change in momentum of body 1 and body 2. So now let us rewrite this equation in that way that we put all momentums of first body and second body, initial momentums to the left and final momentum to the right. So it will be P1 plus P2 equal to P1 prime plus P2 prime. And we see that this is constant value. What does it mean? That the sum of momentum of two bodies which represent isolated system is equal to the sum of their momentum. Initial sum of momentum is equal to final sum of momentum. So regardless interaction between these bodies, which represent a closed system, we didn't get any change in the momentum. So this is the way how you can prove that momentum in a closed system, when external forces do not act on the system or they are compensated, momentum remains a constant parameter. And we considered this case for two bodies, but this can be generalized for many bodies. And for general case, when we have many bodies in this isolated system, we can write that the sum of momentum of each body from I equal 1, from 1 to n, where n is amount of all bodies in isolated system, is always, so this vector is always a constant parameter. So this is the general definition of the law of conservation of momentum for a system with many particles, but we kind of prove this for the system with two particles. Just one thing which I believe kind of reasonable to mention here. I guess should have mentioned it a bit earlier, but doesn't matter. So before when we gave definitions of the change in momentum and force, applied force, we considered that applied force is constant, and also we considered this derivation like the of conservation of energy, that force is constant during this very short interval of time. However, sometimes forces are not constant, and that should be taken into account. So if force is a function of time, then change in momentum is the product of average force, it's denoted like this, to the interval of time. So instead of some instant value, we can operate with some average value of force. And this average value can be determined as follows. So average value of force is equal to 1 over T2 minus T1 integral from T1 to T2, this function which describes the time dependence of force dt. So this how we determine the average force from along the time interval from T1 to T2. And then if we substitute this average force and multiply it by the change in time delta t, it gives us some average force impulse. And this will define the change in momentum. So this is how you deal when there is some time dependence of force and you need to determine change in momentum after some time of this time-dependent force acting on this body. You get the average force and calculate the average force impulse. Okay, this is explained. So we introduced, let's summarize what we have done. We introduced the momentum, describe how change in time of momentum defines force. So it's kind of second law of motion in differential form. And on the example of two bodies, which represent an isolated system, we have shown that the sum of momentum before and after interaction remains constant. So which actually introduces the law of conservation of momentum. Good. So now we need to give a bit explanation what is isolated system in real life, because definitely we don't have such a system of bodies which does not experience any forces applied to it from external environment. And first of all, first case, this is when external forces are compensated. So if we have, again, two bodies, definitely they have some weight next to the Earth's surface. It will be mg1 and m2g. And since they are on some surface, there will be reaction of this surface, N1 and N2. Since N1 is equal to M1G and N2 equal to M2G, they compensate each other. So if we put here vectors, N1 vector plus M1G vector, it will be so-called null vector, or zero vector. Actually, here we can also put not just zero, but zero vector, because we operate with vectors. So correct would be put zero vector. And the same N2 plus M2G will be zero vector. So we see that these external forces, which is in this case the weight and reaction of the surface, they will compensate each other. So that's why, assuming that we don't have any friction between these balls and the surface, this system can be considered as isolated, and the law of conservation of momentum can be applied. So another option is when external forces are much smaller than internal forces. So if this interaction happens like very quickly, internal forces are very large. If there is even some external force, but much smaller than the internal force, again, it can be neglected, and it will not have big impact on the result. So this is also, in some extent, can be considered as a system, as an isolated system. Also need to keep in mind that projection of momentum on different system of coordinates should also follow this conservation law. So if we wrote that P1 plus P2 is equal, like vectors, the sum is equal to P1 prime vector plus P2 prime vector. So if we have some system of coordinates, x, y, for instance, then the projections of these vectors on axis x and y, they should also follow this rule. So that means that we can write P1x plus P2x. So I don't put here vectors because these are already scalar values. projections of vectors on axis x equal to p1 x prime plus p2 x prime. So the sum of momentum before interaction will along the axis x will be equal to the sum after. So this law of conservation of momentum is valid for the projection of momentum vectors on axis x, and the same is true for axis y. P1y plus P2y is equal to P1y prime plus P2y prime. And if you have like three-dimensional case, it is also true. You can apply the same rule for the axis z. So another case which is important and can be useful for considering isolated system. Imagine that we have some platform on rails. We have some rails, and this is view from top. We have some platform on these rails, and there is some rocket on this platform. So it is launched at some angle to the railways alpha, doesn't matter. So there will be some force component of force which is exerted by this rocket on the platform, which goes perpendicular to the railways. So there will be one along the rails and one perpendicular. And this, which is perpendicular, so if it goes along, nothing happens because this platform just moves along the rails and there is no reaction, it moves without friction. But this force which goes perpendicular to railways, platform is fixed on railways, so it cannot move in direction perpendicular to railways. And that will result in some force which is not compensated in the system. So that's why if we have X and Y system of coordinates, the law of conservation of energy will not apply towards the direction of Y, because we have one external force which is not compensated in the system. But since it can move along axis X without any friction, the projection of rocket momentum on axis X plus projection of platform momentum on axis X will be before this launch will be equal to the sum of projections of their momentums after the launch. Rocket X prime plus E platform X prime. So this will be valid. So in the direction of X, there will be no, the system can be considered as isolated system, but in the projection of, in the direction of Y, there will be one uncompensated force, external force, and that automatically makes our system not isolated. That's why law of conservation of momentum does not apply. So this should be taken into account when you solve some problems, because you still can, it will be valid. There is a possibility that it will be valid to apply law of conservation of momentum for one direction, but not to another. But that condition could be enough to solve the problem. And that is another feature of this conservation of momentum. Don't forget that always when you apply law of conservation of momentum, you need to be sure that your system is isolated and there is no external force applied to the system. Okay. So maybe let us consider one example. We will consider collisions in more details, but let us, because there are different types of collisions, so we can maybe start it today and then continue next time. So in general, there are three types of collisions. First one is elastic, so ideally elastic. So what does it mean? It means that during the interaction of two bodies, there is no deformation of these bodies, and there is no transformation of kinetic energy into internal energy. So no dissipation of kinetic energy. And that means that we have simultaneously satisfy conditions for conservation of momentum and conservation of kinetic energy in such system. Then there is another type which is inelastic. And inelastic collision, it is when these two bodies which interact with each other, they stay attached to each other after collision. So their mass, the total mass, is kind of this body which is formed after collision is equal to the sum of sum of masses of two bodies which were involved in the collision. And of course, there is some not ideally inelastic collision, which are most real cases when we have elastic interaction, but there is still some deformation of bodies, and part of kinetic energy transformed to the internal energy and dissipates in the form of heat. So in the course of classical mechanics, so we usually consider two types of collisions, which is ideally elastic and ideally inelastic. So we have a little bit of time, and let's consider one example of inelastic interaction. So let us consider some axis X with two bodies which are moving in different directions, M1 with velocity V1 and M2 with velocity V2. So since it's one-dimensional case, the direction of our velocity will be defined by the sign. So we don't need to put vector here. So these two bodies will interact with each other. So we have M1 and M2, and they will be attached because this interaction is inelastic, and they will move with some velocity v prime. So in this particular case, in order to determine the direction and magnitude of this resultant velocity of two bodies attached to each other, we need to apply the law of conservation of momentum, and we can write m1 v1. So this is positive quantity because velocity is directed along axis x, then minus m2 v2. This one is negative because it moves in the opposite direction, is equal to m1 plus m2 times v prime. So we assume that it moves to the right, but again, its sign will be determined by the ratio between momentum of body 1 and body 2. So we can get the expression v prime, the resultant velocity of these bodies after inelastic interaction, collision, will be equal to the difference between initial momentum divided by the sum of the mass of these bodies. So we see if the momentum of body 1 is larger than momentum of body 2, v prime will be positive. So this system of two bodies will move along axis x. In the contrary, if momentum 2 is larger, this resultant velocity will be negative, so it will move in the opposite direction. So this is the most simple example of collision between two bodies. And next time we will continue with other examples. In particular, it will be elastic collision, and also in one dimension, and also we will consider elastic collision in 2 dimensions when we need to take into account different components of momentum in projections on x and y axis. Okay, if you have any questions, you're welcome to ask. If not, then you can ask next time. We will meet on Wednesday and continue this topic of...
Excuse me, Professor.
Yes?
Can you show the previous slide, please?
Sure. This one?
Yes, yes.
Mm-hmm.
Thank you.
Yeah, you're welcome. Yeah, if you want to spend like more time thinking about this, all these our discussions are recorded and provided on Moodle, so you can access it anytime you want. Okay, guys, thank you very much for attention, and have a good evening.
Thank you. Goodbye.
Mm-hmm. Bye.
Thank you. Bye.
Thank you.
Bye, thank you.
Bye-bye.